Next, we introduce the second application, that is electromagnetic gun. Before introducing the theory, let's first look at a video released by US Navy in 2012. Compared to the traditional gun and rockets, electromagnetic gun has its unique advantages. Its range of fire is longer than that of the traditional gun due to the higher launch speed. It has low cost compared to the rockets, so electromagnetic railgun has attracted close attention of the military. Here we analyze the basic working principle. Please see, in electromagnetic railgun, two rails are powered by a power source. The armature and the projectile in the middle provides a current path. The flow direction of the current is like this. The current is very huge, usually tens of thousands or hundreds of thousands or even mega ampere. With such a current, it will be produced a large magnetic field on the direction as shown in the figure. So the conductor will suffer a force. It's a basic principle of the electromagnetic launch. Through simple derivation, we can find that as long as we increase the current, the repulse force of the armature of the projectile can be increased. Then its acceleration is increased. So in theory, the acceleration of the electromagnetic launch has no limitation. There are two key parts of the study in the field of electromagnetic launch. The first part is the physical and chemical process of contact, which is related to material. Another very important is the power supply, because we need to produce a current tens of thousands or hundreds of thousands or even mega ampere. How to produce such a large current during a very short time period? The basic topology of the electromagnetic pulse power supply is like this. In the figure, IL is the current flowing through the armature. We call the dotted line part in figure the pulse forming unit, which consists of a capacitor, inductor, and a parasitic resistance, a main switch, and a flywheel diode. The work of the circuit is divided into two states. First of all, we give the capacitor a pre-charged voltage, positive up and negative below. At the moment we set, close the switch. Because the diode withstands the reverse voltage, so it doesn't work. The actual working status of the circuit is like this. It is a RLC0 second-order circuit. We design the parameters carefully so that it is a process of underdamping. So the electric field energy stored in the capacitor in advance may be converted into the magnetic energy stored in the inductor. For the specific circuit parameters, we will get a large load current. As we introduced lecture 55 for the RLC0 second-order underdamping circuit, when the inductor current is in the maximum, the capacitor voltage is not zero. After passing the maximum value a period of time, the capacitor voltage is zero. In the actual production process, high voltage capacitors usually cannot withstand a large reverse voltage. So in the pulse forming unit, we design a flywheel diode. That is to say, when the capacitor is going to be reversely charged, the flywheel diode will be conducted and make the whole circuit change into a first-order LR discharge circuit. Next, we will use a simulation to review the basic working principles of the pulse forming unit of the electromagnetic railgun. The simulation of the electromagnetic railgun is divided into two circuits. Please look at the first simple circuit below. This is a circuit with a pulse forming unit and load. In the theoretical analysis, we pre-charge the capacitor the voltage of 10 kilowatts. The key is known that the delay switch at first is 1 connected to 2. Throughout design parameters, 2 connected to 3 at t equals 0, and 1 connected to 2 at t equals 1 seconds. According to the simple calculation, we know that 1 second is too long for the whole circuit. So that is to say the switch is closed when t equals to 0. During the period we are interested in, the switch no longer acts. Then we'll have a look at how to change the current flowing through the load. We start simulation from 0 seconds, and the total time scale is 10 milliseconds. The initial value is set by user-defined. We choose IR2. Please see, at this time, the whole circuit is a second-order underdamping process starting from 0 seconds. The load current reaches more than 40 kiloamperes under the action of 1 PFU. After passing the maximum value a period of time, the whole circuit enters into the RL first-order attenuation process, and the load current continues attenuating. But you can find that the steep wave front and the slow wave tail pulse waveform is not suitable for launch. We said in the process of theoretical analysis that the force of the load is directly determined by the value of the current. So we hope that we can have a smooth load current waveform. In order to attain the purpose, we connected several PFUs in parallel. Look, this is the first PFU. We set its initial energy storage as 10 kilovolts and it's closed at t equals 0 seconds. This is the second PFU. Its initial energy storage is 3 kilowatts and is closed at t equals 0.5 milliseconds. Its third initial voltage is 3 kilowatts and is closed at t equals 1.2 milli. Its fourth is 3 kilowatts and closed at t equals 1.8 milli. All the parallel PFU supplies powers to R4, that is the load. Then we will have a look after the 4 different initial charge voltage, that is the initial energy storage, and the different delay trigger, what the waveform of each PFU and the entire load current. In order to achieve this purpose, we need to see the current form of I5, I1, I3, L4, and R4, respectively. The other simulation parameters are the same as the previous. We look at the current waveform of L1, L3, L4, L5, and R4. Look, this is the delay triggered current waveforms of stage 1, stage 2, stage 4, 3, and stage 4, respectively. The red line is the current waveform of the load. Through setting the initial charging voltage of the capacitor at different stages, that is the initial energy storage and different time delays, the load can attain more smooth waveform, which is requirement of the actual launch.